Hi, I'm Christopher Desert, and I'd like to tell you about our new paper, Limits from the Grave, Resurrecting Hitomi for Decaying Dark Matter and Forecasting Leading Sensitivity for XRISM. This work was done in collaboration with Ben Safdi, his graduate student Orion Ning, and Nick Rod. The Hitomi X-ray telescope was a telescope launched in 2016, but unfortunately was lost after only 1 month. The prospect of obtaining data with Hitomi was exciting because it had excellent energy resolution of about 0.1%, which is to be contrasted with the order 5% energy resolutions of contemporary X-ray telescopes. In particular, this optimizes it to look for evidence of dark matter decay to photon lines, which is predicted in several dark matter models, for example, sterile neutrinos or axions. In this work, we make use of the few blank sky observations, or BSOs, that Hitomi was able to take to show that these BSOs are the most promising path for searching for evidence of dark matter decay. In particular, Hitomi observed a neutron star and a high-mass X-ray binary, both of which emitted essentially no X-rays above a couple keV, and so BSOs are optimal background-free targets to look for dark matter decay in the Milky Way halo. Our Milky Way halo DM profile is NFW with a local density of around 0.3 GeV per centimeters cubed. On the right here, I'm showing the data on the neutron star binned in 100 EV bins for plotting purposes. The background here is entirely instrumental. There are a few points with obvious excesses. For example, in the inset, you can see an emission line around 5.9 keV. We also overlay a dark matter signal example. The energy resolution here is so good that we needed to account for Doppler broadening and Doppler shifting effects in the signal. However, this particular line is instrumental. In our joint analysis over both observations, we find no evidence for dark matter decay and therefore just set limits instead. Here I'm showing the limits on the dark matter lifetime plotted against its mass. In black are the actual limits, and the 1 and 2 sigma expectations for those limits are in red and blue, respectively. This is assuming decays to a single photon plus X. Although we don't improve over existing constraints from other X-ray telescopes, which are shown in gray, our main point is actually that the blank sky searches for dark matter decay improve over that done at the Perseus Galaxy cluster with the same Hitomi telescope, shown in purple, by a factor of a few to an order of magnitude. This is relevant now in particular because the Hitomi recovery mission, the XRISM telescope, is set to launch later in 2023, and it is nearly identical to Hitomi. In that vein, we also forecast limits on decaying dark matter from BSOs of the Milky Way halo from the end of mission XRISM. Importantly for us, it will operate for a long time and make many observations of the blank sky. Although it has a cryogen cooling system that is expected to last at least 3 years, it has a mechanical cooling system that will take over after that. In our analysis, we assume that the full mission is a decade long. Of this 10-year mission time, only 2/3 of that time will be dedicated to usable BSOs. We bin this exposure into 30 annular bins centered on the galactic center, and we assume that the exposure time is distributed in an angle from the GC according to the observed distribution from a 20-year observations of XM Newton, which is an X-ray telescope that observes in similar energy bands. That distribution is shown in the plot on the right. Finally, we assume that all of the observations have background rates equal to that observed in the Hitomi blank sky data, since XRISM and Hitomi will have nearly identical backgrounds. We use this background rate to construct mock data in each of the 30 annular bins. The projected limits we obtain from this data are shown in green and yellow at 1 and 2 sigma. In particular, we expect XRISM to do better than existing constraints for masses below about 20 keV. Even where the limits are surpassed due to the roughly 20 times better energy resolution, we expect XRISM limits to be more robust to systematics than the existing bounds. BSOs have the advantage that they simply reuse observations that will already exist as XRISM accomplishes its science goals, because all observations are necessarily also looking through the Milky Way dark matter halo. Here I'm showing the D factor, the line of sight integrated dark matter density, in each of our 30 annular bins in black for the Milky Way. However, there are other approaches. For example, one could point XRISM at the Perseus cluster, However, Perseus hosts large X-ray backgrounds, and we find that BSOs will be more sensitive than observations of Perseus, which you can also see from comparing the Hitomi limits. One could look at background-free dark matter bright dwarf galaxies, such as Segway 1. However, for any realistic exposure time, under planned observing strategies, BSOs will still provide superior sensitivity. I'll leave it here with our interpretation of our limits and projected constraints on dark matter decay in terms of the sterile neutrino and axion models. Thanks for listening. Have a look at our paper, and please let us know if you have any questions.